Okay, well, hello everyone. So another day, another stream. Today we'll continue our stream on solving problems. So last time I forgot where did we stop, but we were solving bit manipulation problems, and looks like we have a couple more to finish with all the problems here. So I guess we'll be continuing today where we stop, trying to solve 2 out of 3 first. So yeah, checking the stream. Everything seems to be in norm. And we have our first problem. 2 out of 3. Given the 3 integer arrays nums1, nums2, and nums3, return a distinct array containing all the values that are present in at least 2 out of the 3 arrays. Okay, you may return the values in any order. So we have nums 1, 1, 3, 2, nums 2, 2, 3, nums 3, 3. The values that are present in at least 2 arrays are 3 in all 3 arrays, 2 in nums 1 and nums 2. Okay, so that's an interesting one. I wonder how this is bit manipulation related. But the idea for this problem, I feel like the easiest way, I think I'll need the flame shot. Let me add the flame shot. And let's work out this example on our drawing board. So here, so we have like 3 vectors. So let's assume we have the vector 1, 1, 1, 3, and 2. We have the second vector like 2 and 3, and the third vector which is 3. So we need to show the values which are present in at least 2 of them. If you're going with like a brute forcing solution, the brute forcing solution would be something on those lines. Kind of pick the first, which has the most amount or the biggest amount of items. Okay, I think I need to switch to this color. So we'll check this one. So this one has 4 elements. This one has 2 and 3. Okay. 2 and 3. So actually 2 and 1. So we may go with all elements of this one with a for loop. So for I in first, so in this one, so let me call it first. And then go with the second for loop for I in second. For j, this will be j in second. And for k, let it be k in third. In third. If I see I and j or k, this means we have an item in one of the two, and we can add it to the result. So this is an option. I mean, we always can. So we'll have a result array, which will be a vector. So we can always go this route, but this is highly unoptimal. I feel like the solution for this one will be big of let's call it n multiplied by m multiplied by k, which let's assume if they are equal size. In this case, we'll have like a n cube solution, which doesn't feel like a really nice solution for our problem. So we need to think something smarter. Though I wonder how. Maybe because in our case, what we'll need to find it's duplicating elements. But what we can try to do, it's, I guess, I was thinking maybe we should go with such approach. We may try kind of first to concat all the values together, but this will not work. If we go concatenating everything together, because we have 1, 1, which is a duplicate, and this unfortunately doesn't work. Though what we can do, it's we can try to use only the distinct values out of each vector and concat everything together. And in this case, we have like doubles. So probably an algorithm will be something like first getting the distinct values from each array, which this can be done in a linear manner. So we need kind of to do a linear search, get the distinct using a hash set. That's probably the most idiomatic way to do it. Second stage, we will concat everything together. And third stage, we can do a frequency and try to find duplicates or triplicates, or at least duplicates in any order. So yeah, I feel like this will work. So if we try to sum up our algorithm, so first get distinct values, get distinct of all array, distinct of all vectors, concat, result. So this will be like big O of 3 multiplied by n. Let's go this, and this will be like 3n. Concatenating results, that's linear. So it will, yeah, I feel like it's still linear. So it will be like big O of n. And finding duplicates with the frequency, it's still linear as well. So find frequency of numbers. So we'll get a hash map with the results. So for example, in our case, we'll have 1 having 1 count, 3 having like 3 counts, 2 like 2 counts, because here we have 1, 2, 3 threes and 2 twos, so these two. So the end result, we can filter everything which is greater than 2, because this means they come from a different array. So the end result will have it to be like 3 and 2. It also depends on the order. So we have this algorithm, which in sum will be a big O of n. So probably I should move here. So this will be like time complexity. And space complexity will be using a lot more, but also in essence will be big O of n, because we will use a hash set to find this thing 3 times, or it will be like 4 multiplied by n. But this is ignorable, so we ignore constants if we go big O notation, and the space will be like big O of n, so O n time, O n space. If you go with the first approach, still extra space will be big O of n, because we may include all values in the result. So we got from n cube to big O of n as an optimization. But I still do not understand how or why this is marked as a bit manipulation problem. So probably we should have like a bit manipulation strategy. So let me think. Because if we're doing XOR operation, we can find duplicates. Everything else, I guess first stage will remain the same, getting distinct, but the second stage is a little bit more tricky. I do not see a way to do it using bitwise operators. So if you try XORing everything, the end result will be this 1 XOR 3, which is not our answer. Everything else will be collapsed. Yeah, probably we should code first this algorithm, and then we'll try to see in solutions and try to figure out what would be the right approach and why this is a bit manipulation problem. But for now, I do not see it. Yeah, so let's try to code it up. For this, I'll probably need a new library. So let me create one. I'll zoom it a little bit. 2 out of 3. 2 out of 3. So yeah, I'm creating this. I will not need this one. I will need this one. Okay, so I think it's too zoomed, which should be good. So yeah, let me copy this part. Let's create a struct called solution. And let's make sure we disable Copilot, because Copilot will solve it in an instant and makes us will make us cheaters, which we do not use Copilot when we train. And this is a training session. Okay, we have this. Let's add a scenario. So we have a tuple of vectors. I'll just add 3 of them. And we have another vector as a solution. Unfortunately, this kind of problem are tricky to write unit tests because the order is different. When we're using hash maps, the order of insertion it's not necessarily saved, so we can get a little bit different order. But we'll try to figure it out somehow and try to manage. So we have input, but input in our case will be like nums1, nums2, and nums3. So let's try to apply our solution. To our inputs. Yeah. Personally, when I do some operations on vectors, I personally do not like to pass them. Let's call it to move the values to this function. And unfortunately here they will be moved. So if I want to use somewhere else the values above, it will not be possible. In this case, probably a better way would have been to pass them as reference. But kind of the problem is defined this way, so we cannot do much. Okay. I wonder how we can do it in a straightforward manner. Yeah, let's add a couple of scenarios for now. 1, 1, 2. So I think we saw this, it was like 3, 2 or 2, 3, I think. And the last one was 3, and the output was 2 and 3. Okay, so we have first example that's good enough for us to start. As we define our algorithm, first stage we'll need to find the distinct values, and then we need to concat the distinct values into our result. So to transform in the fastest way to find the distinct values from a vector, I would use a hash set for that. So let's use std collections hash set, and we'll need hash map as well, so let me import it right away. So we'll use a hash set and a hash map. So we can do like a distinct first, or distinct one. We'll be passing names1. We'll do iterator, and we'll do collect hash set of i32s. Yeah, unfortunately in this case that would be, we'll need to consume it, so let's use into iterator, because we'll need the values, not the references. So we'll do similar stuff in our case for distinct 2 and distinct 3. So here it will be like distinct 2 and distinct 3. So we've got the distinct values. Now what we'll try to do, it's like concatenating everything together. Yeah, I'm checking. Do I need to zoom it a little bit? I don't know. So let's concat everything together. So distinct 1 join concat includes insert. Okay. I guess the simplest way to use into iterator, and then concat chain. Yeah, what we can do, we need so my keyboard looks like it's so let's chain the other two. So it will be like distinct2 into iterator and distinct3 into iterator. So we'll be collecting. So what we want to collect, yeah, actually at this point, I'm not sure if we need to. Probably we'll do the frequency here, because we can do that right away with the fold and create here a hash map. New. We'll pass a mutable accumulator and an item. So we'll do let entry will be accumulator dot entry dot item insert or 0. Entry plus equal 1. So this will be the way how to do to count the frequency of an item. But yeah, doesn't understand that this is the way. Hash map entry. Okay, so accumulator entry or I guess it's or insert, not insert or. So at the end of this part, we'll have the frequency, but we can go even further. What we can do, it's do into iterator, and we'll have a filter. So here we'll have like a key value path. But we're not filtering the keys. We'll be filtering the values. We'll be filtering the values. Actually, we'll be filtering the value. Yeah. So we do not need the key. We'll need the value. So we will be checking for value to be greater than 2 or equal to 2. This means the value comes from at least 2 different vectors. Okay, so we have this filtering part. Yeah, either we go here with dereference, where we go on the right side with referencing. We'll map our result. In our case, we'll be not using values because we need the keys. So let's map this. I will not need, so we'll be returning only keys, and we'll be collecting them as an vec32. So in hindsight, that should do it. Maybe as a way to do it in one go. Yeah, it's a little bit too much code. I mean, it's big O of n. This should work. Yeah, let's try to run the unit test. Yeah, actually it was expecting to be free too. Yeah, this is what I mentioned, like I cannot assure the order, unfortunately, but it's correct answer. Yeah, let's try to run this in LeetCode. Yeah, this works. I mean, we solved it, and it's quite optimal, but I still am not satisfied. Yeah, let's check first if it indeed works, but it should. We used a ton of extra space using these hash sets and hash maps. Let's run. Yeah, we do have the solution. Let's try to submit it, and I'm eager to learn more about not sure why this goes like that. It's a very weird feeling. Feel like my keyboard is charged. So yeah, fortunately there is no other solution. So for I and Max, yeah, probably this was a mistagged tab. I don't know. I mean, we solved it very fast. Yeah, indeed, our solution is fast. We used with memory for sure. It's not the fastest. We use quite a lot of memory with the hash sets and hash map, but it's a fast solution. For each counter. Oh, so we have here a solution using clone, enumerate, filter map. We have a solution using some bit operations. So okay, wait a second. So constraints 100 and 100. I don't know. I mean, what are all the test cases are using 2, 1, 2, and 3? Yeah, let's check what other solutions are there. No, that's not easy solution. Yeah, this is the first approach which I mentioned, using 3 for loops. But they're not nested, actually. No, but this contains... also, it's a big O of N operation, so it doesn't help, actually. So it's not optimal. Loop and counter solution. Yeah, so we have a counter. Instead of using a hash map, we use this approach. Which it's a little bit less consuming. Count 1, count 2, count 3. I'm not sure how do they handle it's greater than 1. Oh, so this means if a specific number... No, I don't like that. I don't like that. Okay, so can we use to help us quickly find whether an element belongs in an array? And can we count frequency of elements in each array? Yeah, kind of we did that. And I'm not sure about the tag of bit manipulation. That's actually misleading. Anyway, interesting problem. Okay, where we did first letter to appear twice. So let's go with this one. Repeated character. Given a string S consisting of lower English letters, am I in the right tag though? Topics. Bit manipulation counting. Okay. So this is a straightforward one. Let's use a new canvas. We'll try to figure out some ways on how we can solve this problem. I guess the simplest way is as well to go with the frequency. Simple hash set. Once we found, but again, how this is a bit manipulation related, because this is a one-liner. I mean, yeah, we can try something like this. So you can use std collection hash set. So let's create a mutable scene, probably. Be like a hash set new. So we go with the string as bytes. Yeah, as bytes is usually a little bit faster than if we try to use chars, but it doesn't really matter. Or yeah, the most idiomatic way, output C will be like a full byte in this. If scene has or contains, I think it's contains a byte, then we do a return byte as char. Okay, so we have this. Else we scene insert byte. So we'll be inserting the byte part. Fortunately, this will not compile because we need to have a return statement on all our branches. Yeah, so I guess the other part will be like panic. Should exit before. This will make it compile. Casting as char is invalid. Yeah, we need unfortunately to dereference. We cannot cast a reference to a valid type. Yeah, so this is solved kind of. It's an idiomatic way on to find duplicates, or the first duplicate, or all the duplicates. But the question is, how can we do it with in a bit manipulation manner? How can we do it? Yeah, let me submit this first. Yeah, it did work as expected. A little bit more memory than I wanted. Yeah, let's try solutions in our case and see. I want to see Rust solutions. Capacity, blah blah blah. Skip while. Yeah, I mean that's the other way how to write the same code, but it's not a bit manipulation tag, unfortunately. So this is as well misleading. Let's check out the solution. Maybe there is some Rust bits 100%. So approach hashing, time complexity, space complexity, same manner as I did, exactly the same. But instead of hash set, he uses a hash map. So nothing new here. Yeah, probably that's a mistag. So what can we do? let's refresh the page and continue. So we are 30 minutes in. Today I think I'll have a shorter stream, like 1.5 hours, no more than that. Okay, so prime number of set bits in binary representation. So yeah, let's check this one. Okay, so given two integers left and right, return the count of numbers in the inclusive range left right having a prime number of set bits in their binary representation. 2 is prime, 3 is prime. Yeah, so now we'll need to recall the prime algorithms. Yeah, let's check. Okay. So left, right could be from 1 to a million. And right minus left, what does it even mean? It's 10,000. Oh, okay, so we can get 10,000 numbers, but the range will be up to a million. So we need to find prime numbers till a million, if I understand correctly. Yeah, that's a tricky one. I don't recall now any algorithm. I'm not sure why my keyboard it's electrifying me. Have it metallic. So something is not right in this part. Okay, so how can we do this? What does a prime number look like? It's divisible only by himself. So I'll need to find some prime number algorithms, because now I do not recall any in my mind. Okay, anyway. So probably what we will do, we will need a new VS Code session. Yeah, let's create a VS Code session. Minus sleep, and we will have the value, what's the problem called? Prime number of set bits in binary representation. Prime number of set bits in binary representation. So let's go there. Prime number of set bits in this part. I will not need this, I'll need this. Yeah, I'm not sure. I kind of need to figure it out. What's the trouble with my keyboard? So let me try to connect and disconnect it, because I cannot use it right now. It's really tough. So I need to get under my desk and try to connect and disconnect my keyboard. Okay. So yeah, now it looks good. It looks like my camera didn't find me, and started to struggle. Let me connect it again. Okay, so now it doesn't shoot me with electricity, so that's good news. Okay, so I'm back. Let's try to do this part. So we have this. Let's add a couple of scenarios. So expected from us will be left and right. So it will be like 6 and 10. Yeah, actually this should be a tuple. And the answer will be 4. So we'll have here left, right. Solution. Yeah, it doesn't see it yet. Solution. I feel like a Pavlov's dog. I'm afraid of clicking my keyboard now. Okay. So I have this part set up. This actually I can full screen mode. Will not need this. Okay. What we can start doing, it's creating the range, and out of this range, try to count the number of bits. So I guess our problem will be something on those lines. So we'll have our left, right. I feel like this should be included. So this is how in Rust you'll be creating a range. The Rust. Hello. Should I answer in Romanian? Pot să răspund și în română. Îmi place Rust că e un limbaj fără garbage collector, destul de complicat și e un challenge pentru mine. Da, la final de zi nu prea contează în ce limbaj rezolv problemele, că înveți tehnicile și anume algoritmii. Algoritmii nu diferă de la limbaj la limbaj, adică poate tehnica de scriere o să fie puțin mai diferită, dar în general odată ce ai învățat, ideea, adică cum să cauți frecvența sau cum să găsești ceva unic, să faci traversal la un graf, atunci nu mai ai nevoie de chestia asta. Adică nu mai o să scrii în oricare limbaj. Nu mai ai nevoie de partea de limbaj, adică nu o să depinzi. Scrii și în JavaScript, poate puțin diferit la structură, în Python, în PHP, în oricare alt limbaj. But yeah, let me get back to English, because this is an English stream though. So yeah, we have our range, like left and right. Now what we'll need to do, it's we'll need to map the output in the form of like number, And there is a function in Rust called count once. Da, sigur. El poate să pornească și pe Raspberry Pi. Dacă fac un așa off topic, să zicem. Where is the layout learning? Is it this? Not this. Welcome to Rust. I think it's this. Yeah. So there is a tutorial called Comprehensive Rust, written by Google guys, and it has like 3 parts. So one is Android, Chromium, and bare metal. So if you're interested in let's say low-level programming, you can check the bare metal part of this tutorial. But Rust, yeah, can be written to any microcontroller. Actually, it's quite popular on some of them. Though actually I spoke with people which are working with microcontrollers, and they still do not use Rust. They write in C. Yeah, I personally do not write low level and microcontrollers, but all answers, what you can check, it's using this part. So it's a very good tutorial. I think we have our Telegram channel, so let me send it to you there. Where is my Telegram? I feel like I did something. Yeah, looks like my Telegram doesn't start. Yeah, let me start again. I'll send you the links there. Doesn't want to start. I'm not sure. I broke Telegram, looks like. Okay, so this is the first one. And the second, it's to go to rustlang. So their official site, and they have like a Rust part using embedded devices. I personally never dive deep here, but you can check this part as well to see more details on how to write on embedded and microcontrollers. But yeah, let's get back to this problem. So here we have our algorithm to find the ones. The second part will be to filter them out and find is prime ones. So probably, yeah, let me do it. I'll have it like an FN, so it will be like is prime. We'll write down later, and we will count how many. So as I32. What did I do? Yeah, looks like I good. Okay. Good. So yeah, let's write the is prime algorithm. And nothing comes to my mind because I feel like a prime is not a fast way to go. Yeah, how to find if a number is prime or not. Yeah, I've written code like this. Okay, type mismatch, a bool to do. It doesn't allow me to do it like this. Why? Type mismatch in a function. Oh, so it expects an U30. It expects an U32 because it will be a count. Okay. Of reference of this. I mean, okay, so we can forever. Yeah, probably, yeah. Maybe I'll do a dereference here. Oh, okay, so it doesn't really matter. At this stage, we can dereference it here to get a value. So yeah, we have we did outline the algorithm. Now we need to write down a prime function, which I don't recall. I feel like we should try to see if it's divisible by 2 or something. Oh, I really forgot. I mean, yeah. Let's check prime number algorithm. I think it's Euclid, if I'm not mistaken. Euclid lemma. Euclidean algorithm. Oh, Eratosthenes. I recall this part, but I forgot how to what it is exactly. Okay, so this is one of the most optimals, if I recall, ways to write a prime algorithm. Up to a given limit. So kind of we'll need to find the prime numbers till a million. Yeah, I'm not sure because this doesn't feel very optimal though. That's the trick. Prime divide by 2. Divisible by 2. Yeah, I mean, a long time ago, I did write some algorithm like find if it's divisible by 2. But that was not very optimal. So is integer n greater than 1. All prime numbers from 2 to n. So probably probably what we should do. What does a million mean? A million means we'll have at most, because we can write them by hand. This is what I mean. Yeah, let me go to this board. So our constraints start at yeah, we'll not need to write a prime algorithm, so that's good news. So we'll be looking at the constraints. So we have our range, but what is minus given return the count of numbers in inclusive range left right, having a prime number of set of bits in their binary representation. For example, 21 is binaries 3 set bits. Okay, so we have our range starting from 1 to a million. So 1 to a million, 10 power 3. But what exactly this means? Because the biggest number, if it's a million, this will be like 2 power. I forgot what number. So let's see. 2 power 5. That's 32, if I'm not mistaken. 64. 7. Yeah, I guess 2 power 10 will be 1024. 11, 248. 4, 96. Let's say 9 or 892. 10 power 6. Yeah, I mean 10 power 6, that's good, but we need it in a binary representation because I need to know what will be the max number of 2s. But wait a second, I think they gives us in the hint. Yeah. So they gives us this part. So I assume 2 power 19 will be close to a million. Yeah, 2 power 19 will be close to a million. So let me do a short test. Fn test. Yeah, let's call it test. So let's print. Let me print. So 2 power 19. I guess should be like I power or power I32. Let's say 20. Yeah, so between 19 and 20. So I guess at most we can have like 20 bit set. So if we go similar approach here, so this will be like 11, 12 bits max set, 13 max bit set, and like 20 will be that number, a million or something like that. 1,048,576. 576. So this is our range. Yeah, this should be 10 power 6. Yes, sorry, didn't see it at first. So at most we may have like a 20 bit set. This means if you write it in a binary form, we'll have like 20 ones. We count the ones and we may get here. So we may write by hand like the lists of prime numbers. Here we can hard code it. Actually not const, let me use the let primes. So we can write like 2, 3. Probably I'll copy this. It will be like a little bit faster. Yeah, what will not work. So we'll return like primes contains n. So this should do it. Yeah, this works. So it was a pretty fast one. Yeah, probably I personally don't really like it in this form. Maybe I should do it in one implementation as a private function. And here we'll be writing like a self x prime. So this should work as well. Yeah, there is another trick. We can do like a cargo clippy. To see if there are optimization we can use. Yeah, actually we may not do a vec. We can try to use this structure, more like a constant point. So this is a little bit more optimal. So yeah, using cargo clippy, it's a useful thing to do. Shows different optimization techniques which you may apply. So that's really powerful. Okay, so we have our solution. Yeah, as well, I do not understand how this is bit manipulation. Oh no, this one is bit manipulation related because we do the count ones part, which is there is a function in Rust. Probably another approach, we should divide by 2 or shift bits right, which will be exactly the same way, and count the last bit and see which value. Do Rust code style encourage or line function body vector contains? You mean this part? Yeah, if it does encourage, I mean, yeah, I personally like it to write a small function like this, like is prime, because this reads better. The entire algorithm reads quite well because I see here I have a range, I have a mapper function, and I have a filtering function. What does filtering function does inside? Um, it's like a small abstraction. I don't need to get deeper. So this probably it's like can be written here without any troubles. But imagine if this was like something more, where a bigger algorithm or more complicated one, then this structure I like more because here I look at the main algorithm. I have an idea what does it do. And if I want to get into details, I will get inside. There is optimization like writing an inline tag to mark some specific function to be inlined at the compiler level, to not be compiled as separate function. It's like micro optimization, like 245 contains n. What do you mean this specific part, like with contain? Yeah, I guess if you want to be if here we had like a ton more values, I would not go with contains. Imagine if we have like thousands or millions values here, because contains, I'm not sure about the exact implementation, but if I would write a contain function, I will do it in a linear time, because I will need to go with every element, check, compare with this and this and this and this, and this is not optimal. But in our case, we have like 8 values, so contains will be a constant time, so it will be a big O of 8 at most. It will be like we'll check all these values, so it's still linear time. How to do it in a linear time? Instead of primes written in this form, I would use a hash set, and I'll check if the value is in the hash set. So pretty much I'll change the data structure, but I gain time like by a ton more. Oh. Okay. So let's try to submit this. Yeah, so looks like we have a pretty fast solution. Yeah, let's check. Yeah, counting bits. They written their own counting bits, and they wrote their own is prime function. Okay. Okay, just a simple question. Go ahead. Okay, so yeah, I guess we are the fastest, mainly because we are using count once, which is a function provided by Rust. So this is why we are the fastest, I think. Yeah, I don't need this. Yeah, let's check the next one. Check if bitwise OR has trailing zeros. Yeah, let's see. Do we have time for one more? I think I'll solve this one, and because I wanted to do a shorter stream today. You're given an array of positive integers nums. You have to check if it's possible to select 2 or more elements in the array such that the bitwise OR of the selected elements has at least one trailing zero in its bits representation. For example, the binary representation of 5, which is 1 or 1, does not have any trailing zeros. Okay, so this one has a trailing zeros. Has 2 trailing zeros. Okay, so that's an interesting one. I see the acceptance rate dropped a little bit. So let's see. Bitwise work can never unset a bit. If there is a solution, there must be a solution with only a pair of elements. With only a pair of elements. We can brute force the solution and enumerate all pairs. So yeah, I was thinking to enumerate all pairs first, and then out of these two, find the trailing zeros, at least one trailing zero. Let's check the third. As the least significant bit must stay unset, the question is whether the array has at least 2 even elements. As the least significant bit must stay unset, two even elements. Okay, so they gives us a hint. We should look for to add even pairs. Yeah, let's check a couple of examples and move to our drawing board. Output true. If we select the elements, yeah, let's get to our drawing board and try to brainstorm there. Yeah, looks like my keyboard started again to shock me. And I don't understand why. I don't understand why. But okay. So let's use a new board here. We have this part. We move it here. So first iteration, I guess we try to get our pairs. So if you have like a 6, which has a binary representation with one trailing zero, but how many trailing zeros do we need? Has trailing zeros, whose bitwise OR has trailing zeros. Okay, so if we go with the following lemmas, were ideas. So idea number 1, it's like if we go with 1 0, this will be the representation. 4, so this will be like 2. This will be like 4. So these are even numbers. So even numbers will always have a 0. And odd numbers, is there any odd number which doesn't have a 1 in the end? Yeah, let's try 7, for example. What will be like 7? So it will be like 1 1 1. 4, 6 and 1. So it has a 1. So we will need to filter out yeah, we'll need to filter out only odd. So I guess the simplest possible scenario how to write it down. Yeah, the following lemma. Yeah. No, we don't even need to do it like this. We don't even need to. We just need to find all odd items, and not even all odd items, but we need to find only 2 odd items in our nums. And the moment we found 2, we got the response. Because yeah, the idea is bitwise OR cannot unset a thing. So for example, we'll have trailing zeros only when we do bitwise of two even numbers. Even, so even 1, bitwise or even 2, only then we'll have a 0 at the end. If you do bitwise with two odd numbers or odd even, it doesn't matter, because this one will have a 1 always as the last number, and this one will have 0. So 1 or 0 will be 1 in the end. So we do not have a trailing 0. So I guess the simplest possible way is to find two even numbers. If we found them, then we should return. So we have this part. So we'll do like nums iterator filter. Here we'll be writing x modulo 2 equal 0. Take 2. Yeah, I'm thinking how to write it in a more idiomatic way. I guess take 2. And collect maybe. Yeah, so this will be like a vec of i32s, and here we do result len 2. Yeah, because this is yeah, unfortunately that's a sad way to write, but okay, so take can build from iterator of elements of yeah, personally don't care if this is a reference or not, because I just need the len part. But yeah, why do I do it like this? I don't need to collect, I just need to count. So let's count. It'll be like u32, and the count part if the result yeah, okay, result equal to, then we are good. So mismatch types, found usize. Oh yeah, oh, we don't care. Okay, so sorry, move len equal to into separate function. Len equal to, you mean this part? I can, but that would be like a little bit of an overkill. So I may move this part in a separate function, because this is ugly and reads not very nice. But that's a little bit of an overkill. Never mind. Okay. Okay, so it looks like there are solutions faster than ours. Let's check. Even counter. Okay, similar approach. I mean, they figure it out. Filter, take 2, count. So it's a similar approach. Not sure why that one is faster than this. Yeah, let's check this one. Maybe iterators are a little bit slower. I don't know. Algorithm wise, it's similar. Yeah, if I resubmit, maybe I have like another. No, it's still 3 microseconds. I don't know why it's slower. It's literally the same, but doesn't really matter. Okay, so yeah, let's move on. A number complement. The complement of an integer is the integer you get when you flip all the zeros to ones and all the ones to zeros in its binary representation. So pretty much we need to invert it. For example, the integer 5 is 101 in the binary, and its complement is 1 0 1 0. Okay. So how can we invert all bits? So to invert a bit, we can use XOR operation with 1. This will invert it. Okay. XOR to 1. Yeah, probably we should do a little bit of research here. Little bit of research. Yeah, I'm not sure if I have time for this one. So I guess we will, because I planned for an hour stream. So probably I'll do another stream on Friday, and I'll pick from this one. Yeah, the idea here is we kind of need to invert it. So there are multiple ways to shift every bit with negation. Yeah, that's but we'll need to collect them and shift them back. So probably there is an idiomatic other way. Because if we go with here 1 0 1 0, so we'll have, yes, something like that. I mean, we will first thing we'll need to get the bits. We can shift them right and inverse them. So to inverse a bit, we can use like XOR. And then we need to store the results and set them back, the result in the proper order, and formal number. So something on those lines. Yeah, this one is not trivial though, for sure. Topics, bit manipulation, complement of base 10 integer. Yes, shift +1, condition for special cases. Yeah, oh, okay, so I feel like we will stop here and we'll continue next time. We'll plan it for Friday, same time, 8:30. So yeah, thank you for joining in. Un oarecare, probably you are the single chat member. At most we had like 5 people joining, but they disappeared. So yeah, thank you everyone, and thank you Un oarecare. So bye bye. Let's continue on Friday with this problem.